In this lecture, we are going to look at a new type of op-amp called the folded-cascode op-amp. Before we do that, let us first quickly see why we need a different kind of op-amp. So the cascode op-amp seems to do most of the things that we want to do. So let us quickly see if there are any drawbacks. So let us quickly draw the structure of the folded cascode op-amp that we have been seeing so far. I'll use the NMOS version for illustration. And let us say that the bias voltages are as shown. So gate of M0 gets a voltage VB0, gate of M3 and M4 get voltages VB3, gate of M5 and M6 get a bias voltage VB5, and this is the output taken at the drain of M4 and M6. And V1 and V2 are the inputs. This is our standard structure which we have seen for the telescopic op-amp. Now we want to see what the issue with this is. So one of the most important issues can be seen if you apply unity gain feedback on this particular op-amp. So in other words, I am building the op-amp in this structure. I am trying to build a unity gain structure from this op-amp. So I want V out to be equal to V in. So I'll have some DC value, and on top of this I'll have some certain swing. And at the output I should get an exact replica for both DC and AC. Now let us look at what will happen in this case. The first thing we need to see is whether the bias point is correct. And it turns out that the bias point would be perfectly fine for this op-amp. But the minute you apply the swing, it turns out that there are some swing limit issues with this particular op-amp. So to illustrate that, I'm going to call the voltage at this node Vx. So let us try to find out what are the maximum and minimum voltages at the output node in unity gain feedback condition. So the maximum value, so let us say VO is now starting to increase. So as VO starts increasing, as you can see, Vx is at a constant voltage, which is given by VB3 minus VGS4. So Vx is always at this constant voltage, of course, I am assuming that there is a total current 2 I0, so that there is a current I0 each through M1, M2, M3, M4, etc. Okay, and this is the value of Vx. Now, the maximum value of Vo will occur when M2 hits the triode region, because as you can see, the gate of M2 stays almost constant at Vx. And the drain of M2 stays almost constant at Vx, but the gate keeps increasing. So eventually this transistor M2 will reach triode when M2 goes into triode, and that will happen when the gate becomes larger than the drain by a value of VTH2, so VT2. So that will happen at this condition. Now what about the minimum value of the output voltage? So now let us say that the output is decreasing. So of course M2 goes further and further away from triode, but let us look at M4 now. So if you look at M4, transistor M4, you will see that its gate is constant at VB3, but the drain voltage keeps dropping, and that means that eventually M4 will hit the edge of the triode region. Now when that happens, the condition on the voltages will be VO min, the minimum value, can hit one threshold voltage below VB3, and that is given by VB3 minus VB4. So now we have found out the maximum and minimum values for the output voltage. These two voltages will determine, these are the common mode ranges at the output with this condition, and with this we will be able to figure out what the total swing, allowable swing at the output is. So VO max minus VO min, and that is equal to Vx plus Vt2 minus Vb3 minus Vt4. So the output swing is nothing but Vx plus Vt2. So Vx is Vb3 minus Vgs4 and the minimum value is Vb3 minus Vt4. And this is nothing but Vt4 minus Vgs4 plus Vt2, and please note that this particular expression is nothing but minus Vdsat4, and therefore this is nothing but Vt2 minus Vdsat4. So this is the maximum swing allowable at the output. As you know by now, for typical values of transistors, this may be a few hundred millivolts, let us say 0.5 to 0.7 volts. And we know that this is of the order of a couple of hundred millivolts. So you can see that this swing limit is completely independent of the supply, and this is only of the order of maybe half a volt or so, irrespective of how large a supply you can get. So there is a strong swing limitation in unity gain feedback. So this is a classic problem with telescopic op-amps. Now we want to figure out how to fix this. Hence you need a different type of op-amp. So now we will redirect our attention towards the other kinds of cascode structures we have seen before. So remember, the cascode structure can primarily be broken down into a common source plus a common gate structure. So that is exactly what a cascode structure is. So you have two transistors. The input is applied to the gate of the common source structure, and you cascade a common gate structure along with this to give you better output impedance and so on. There are very attractive qualities for the common gate structure. So I'll call these transistors M1 and M2. And in this case, I have shown a common source NMOS and a common gate NMOS as well. So both these transistors are NMOS, but please note that as far as the signal picture is concerned, the NMOS and PMOS are identical. They have the exact same small signal equivalent circuit. Therefore, you should be able to realize a common source common gate combination where each of these transistors could be of either type, and therefore we come up with 4 different types of cascode structures. So this is the first one, which is the NMOS cascode. Of course, if you were to draw the PMOS cascode, which we have also seen before, this is the PMOS common source followed by the PMOS common gate, and you have 2 more structures. The first one we will look at is the case of an NMOS common source structure followed by a PMOS common gate structure. So the way we can draw it is since we are used to drawing the PMOS with the source side up with VDD on top and ground on bottom, I'll draw it in this manner. Maybe there is a load resistance RL, which I'll show like this. Now you also need a bias current source for these 2 transistors, and that will be shown as a current source from VDD. Let us say this is some I0. And of course the gate of the PMOS transistor M2 is connected to some bias voltage VB. Now what are the bias conditions of M1 and M2? So as you can see, if M1 needs a bias voltage at its gate, which maybe I will represent as VB1, and this will cause some current I1 to be the bias condition for M1. So therefore the current through M2, which is I2, is given by I0 minus I1. As you can see, the NMOS is biased as the difference between the current source I0 and the bias current of M1. And needless to say, you should apply an appropriate VB and of course VB1 at the gate of the PMOS transistor M2. And the 4th structure is the PMOS common source followed by the NMOS common gate structure. So this is the common source NMOS, common gate PMOS, and you can also build a cascode structure with a common source PMOS transistor plus the common gate NMOS. This is the 4th version. I will leave it as a homework exercise. It is a pretty straightforward extension of this particular structure. Now, what is the big difference between the folded cascode structure? So these structures, maybe I'll call them 1, 2, 3 and 4. The point to note is that 3 and 4 are the so-called folded cascode amplifiers. Why are they called folded cascode? Because the way we draw the circuit is such that the circuit is folded down, the current is folded down into the common gate PMOS structure from the NMOS. So that is why these are called folded cascode amplifiers. Now, what is the advantage of the folded cascode amplifier? So as you can see, in the case of the regular cascode structures, which are structures 1 and 2, in the case of these regular cascode structures, the bias point of M1 at the input, which may be VB1, and VB are intimately tied together because VB decides when M1 goes into triode. Therefore, the input and other bias voltages in the amplifier are somehow related, whereas such is not the case in the folded cascode amplifier. So maybe let us quickly take this structure and let us try to come up with some expression on the bias conditions for this particular amplifier. So let us take this folded cascode, and now let us modify this, because I know that there are no ideal current sources. So this current source is a bias current from VDD flowing into this node, so that is clearly generated using a PMOS transistor. Maybe I'll call that M0, and this current is I0, and of course the gate of this current source is going to be tied to some voltage VB0. Now, of course, the bias conditions VB0 is decided by what current you desire. So that is decided by I0 and of course the size of M0. What about VB1 is decided by the value of I1, that and of course the width of M1, that also decides parameters such as GM and so on. What about the current through what about I2 and M2? How do you decide VB2? So it turns out that there are a certain range of VB2s that can be supported by this particular amplifier. So let us see what will happen if I start changing VB2. Let us say I start increasing VB2. So in this structure, as you can see, if you apply KCL at node X, okay, so if you apply KCL at node X, you can show that I2 is always the difference between I0 and I1. And as long as all transistors are in saturation, this current will not change appreciably, which means I2 is constant. Therefore, if I2 were constant, what this means is that the gate source or the source gate voltage of M2 stays constant, which means the voltage at node X starts increasing. So as VB2 increases, Vx increases, and at the same rate. And please note that transistor M1, so transistor M1 here is moving further and further away from triode, so you are in no danger of moving that. It has a constant current, so there is no problem with the bias point of M1. But please note that transistor M0 is moving closer and closer to triode because its gate voltage is constant and the drain voltage is increasing. So M0 moves closer to triode region. So M0 clearly moves towards the triode region, and eventually it will go into triode. So the maximum value VB2 max is clearly given by VSD sat of 0 plus, it's given by VDD minus VSD sat of 0 minus VSG2. So in other words, this voltage is at VDD. So at the edge, this drop will be VSD sat. VSD sat 0, and this voltage is VSG2, and this will be the maximum value of VB2. What is the minimum value of VB2? So let us say now that VB2 starts decreasing. As you can see, Vx starts dropping, and eventually one of two things will happen. If Vx starts dropping as VB2 drops, eventually M1 could go into triode, or the other thing that could happen is that M2 itself could go to triode. As you can see, the drain of M2 is being held constant, but the gate keeps dropping. So one of these two will happen, and that will purely depend on the exact bias condition. So now that we have a basic understanding of how this folded cascode works, let us quickly go ahead and build the op-amp out of this folded cascode. Clearly, we built the telescopic op-amp using the regular cascode. It should be possible to build an op-amp out of the folded cascode also, and that is exactly what we are going to look at